All right. So, hello everyone. Thanks for coming to the AI and medicine workshop. This is just going to be an introductory sort of overview to gain, I guess, some intuition into how AI works, what it is, and how it can help us as medical professionals. Yeah, so we're just gonna talk about some state-of-the-art things, perhaps do some discussions, and I have a couple cool demos that I think will be fun. So just a quick introduction. I think I know everyone, but name's Hamza. I used to be a roboticist and an engineer before I did deep learning. Um, Professionally deployed a few models, and I'm just interested in intersectionality between AI and medicine. So our agenda for today is we're just gonna introduce this concept of AI, talk about history, because history is very important for for us doctors. Um, talk about what it can do realistically. There's a lot of hype around AI. I think we really need to understand what it can and cannot do, because there's a lot of things it can do. And we're just going to talk briefly, just very briefly, about how it works. Nothing too technical. Then we're going to do a couple demos. So, well, what's artificial intelligence? I just pulled this definition from a book: machines that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. So I really like this definition because it describes something that a lot of people miss is this intelligence that we perceive in AI doesn't necessarily have to be, the same kind of intelligence as us humans. We just perceive it that mimics our cognitive functions. You know, in short, it really is just very complicated, complex function that does things that a simple if statement or simple, what you'd perceive as classical programming can't really do for us. So, you give it, for example, an x-ray, and it tells you whether someone has pneumothorax or doesn't. So that's when you get into kind of complex functions, because an x-ray is very complicated. There's lots of information there. How do you process it? It's really tough for us to give rules to a computer to kind of classify these things. But if we let the machine kind of figure out these things by itself, by having a data-driven approach, then we start getting into what we call artificial intelligence. Now, there's different ways to classify AI, but I like this simple classification here. Most of what we have right now, or pretty much everything, is what we call our narrow intelligence or weak intelligence. So that means that, the AI we're using only does one thing and it can't do anything else. So for example, you give it a picture of a dog or a cat, you're like, okay, is this a dog or a cat? Or for example, an AI that drives your car for you. So right, so it can only do driving cars, and if you give it, a game of chess, then it can't do that. Or perhaps like any of these other tasks that are unrelated to the primary function, they would not work. And pretty much all AI right now is at this stage, very narrow. It does what it does perhaps better than a human, but it can only do one thing really, really well. So think back to the, chess AIs that can beat world champions, but this chess AI can only do chess. Now, the next step up would be, artificial general intelligence, short AGI. So this is sort of like your ideal AI that you can talk to it. It thinks like a human. It can do multiple things. It can pretty much learn any task. So it can be good at chess and drives cars and can be a doctor at the same time, right? So if you're thinking to examples from fiction, in Marvel's, what's that red robot? I don't remember. Vision, yeah. It's like Vision. And then you get, the next step up, artificial super intelligence, which is essentially an AI that is so much better than a human at cognitive functions. Sorry? Hello?
No, never.
Okay. So yeah, so an artificial super intelligence would be essentially like scaled up, can do anything, can learn anything, has access to unlimited resources. So sort of like think Ultron from Avengers again. So yeah, an ideal case for us would be an artificial general intelligence. It's actually intelligent, can solve many, many problems, and doesn't sort of like supersede us humans. So, that's one way to classify AI, but another way to look at it is and this is from a paper for short guide for medical professionals in the area of artificial intelligence. Kind of recommend it. It's very short. It has nice visuals, explains things really well. It's a good and easy read. So they sort of they show these classifications of machine learning methods. So we've got supervised learning, and you'll see here we have a kid picking up blocks, okay, and learning to put them into bins. Now these bins are essentially labeled, and the hope is the child can match the circle with the circle, the triangle with the triangle, sort of like figure out an association. And that's what we do with most artificial intelligence models. So we show them an example of a dog, and we tell the AI this is a dog, right? We show them an example of a car and tell the AI this is a car, and then if you have a large enough data set, then the hope is it can generalize and learn on its own. So most AI models nowadays are supervised, the useful ones at least. But there are other classes. So unsupervised learning is when you still have these blocks, but you don't leave labels on your data bins essentially. So imagine you're giving an AI pictures of dogs and cats and planes and cars, all that stuff, but you don't tell it what it is. Like you just give it pictures and hope that it learns the difference between them by statistical methods or whatever. We're not going to go into details, but this is when you have too much data, I guess, for you to label. So I mean, imagine you have 1 billion images. You're not going to go through each of them and tell the AI, okay, this is a dog, this is a cat, this is a plane. You're gonna essentially give all these images to the AI and hope that it can tell the difference by detecting different features in each sort of like class of objects. By the way, if you guys have any questions, please feel free to interrupt me and add your own vignettes or ask questions. And finally, we have reinforcement learning. This is interesting. I don't think any of us will use an AI that actually uses reinforcement learning anytime soon. This is sort of like the holy grail of robotics. It's essentially if you think back to your classical conditioning from your psychology class, this is exactly that. Essentially, giving the AI, a sort of actions that it can do, asking it to do an action and then giving it feedback, either positive or negative feedback, and hoping that it learns to do better actions. That's in a nutshell. I'm not going to go into technical details. And then finally, you'll see deep learning is classified differently. And it has this weird, yeah, artsy looking image. The reason they have this, I guess, this figure here is to show you that, with the introduction of deep learning, we don't just have simple labels on things anymore, right? So we don't have just, oh yeah, match the circle, the square with the square. Deep learning can look at the real world and all its complexities. Let's say you can give deep learning your sort of an X-ray and history, and a few other pieces of information. It can process them all and look at sort of the nuances and complexities, what we call the non-linearities between all these pieces of information. Okay. And deep learning actually does fall under all ABC categories. It's not really a separate category by itself. It can be used in either A, B, or C. So just a brief history to give a context into where we are on the curve of progress. It talks of machines that learn have been since computers were invented, right? So since the early 50s and 60s, they actually invented the model for the neuron that we use now. So if you have heard of neural networks, the ones that are used in ChatGPT nowadays, this, like, the basic neuron was invented back in the 50s, right? So there it has a long history, but there hasn't been much progress until recently, and we'll talk why. But essentially, think back to the era of trying to make a machine that can beat a chess champion, or yeah, essentially that was most of AI. Just because usually approaching a toy problem helps you discover things in computer science. That's how they do it. And then, with the era of the internet, we started formalizing sort of machine learning methods that are statistical in nature. So if you've ever heard of linear regression, if you're in your statistics class, that's sort of one of them. This was most useful for like detecting spam emails, especially in the early 2000s. So the field was going along well. It went through what they call the AI winter, where people realized, there's too much promise. That was back in the 90s, essentially. That, there's too much promise in AI, but it's not actually doing much for us. So people pulled back funding for it. It wasn't moving along very well until the 2010s. So 2011, there was a paper from U of T actually, that, like, we have these neural networks that were invented all the way back, but weren't very useful because we didn't have good computers. Well, now we do. So essentially, they applied this old, concept of neural networks on modern computers. And, there was a deep learning explosion after because it worked so well. And the past 10 years, there has been insane progress. So most of the progress in deep learning happened in the past 10 years, which is kind of scary because we could be essentially on like the beginning of a sigmoid curve of progress in AI, that we don't know. So we don't know how much we can take AI like further in terms of how useful it can be for us. We just don't know yet. So it could be that we explored everything that can be explored in AI, and it's not going to get much better, or it could be that it's just getting started. It's just very recent with deep learning. So again, it's the same graph, but essentially, tells the story a little more formally. in early, in 50s and 60s, they're like, oh, we have computers, let's build intelligent machines, right? And then in the 90s, they're like, oh, let's slow down, let's not overpromise people, because they did, and that resulted in what we call the AI winter, essentially. And then the 2010s, it actually started to gain some tractions. And people, like, I heard stories of like people were like disrespected in their departments and weren't given funding, and then suddenly, after 2010, they became millionaires, and companies fighting to hire them. So it's pretty recent. Now, specifically for us as medical students, I just wanted to show essentially like deep learning studies on PubMed, and you'll see that recently there's been like essentially like an explosion in publications, right? So the biggest ones are pathology and radiology, and this is just because in between 2010 to 2020, most of the AI that we had was really good with images. But now recently with ChatGPT, we're getting AI that's actually good with text. So I think this will change. I think it will essentially spread to every field in medicine. And we'll see, like, if you're concerned with publishing papers, get an AI, because you'll be able to get a lot of good publications. More publications equals more people citing you, right? So um, just so you know. All right, so let's talk about a history of ChatGPT specifically, because I think actually, first of all, is anyone here not familiar with ChatGPT or hasn't used it? Um, Okay, I don't want to regurgitate what you saw on your TikToks, or maybe you tried it yourself. So, just, ChatGPT answers your questions, can talk to you, it's pretty intelligent. But what's crazy is the paper that was a basis for ChatGPT was only published in 2017. Like before then, the architecture for essentially what's called a transformer did not exist. So it's very, very recent. And ChatGPT is just a scaled up version of the transformer that was published in 2017. So they didn't even change it. They just took what the technical details in that paper and scaled it up like by a million or billions, actually, billions of neurons, and it worked really well for some reason. So yeah. Now, let's talk about what can modern AI realistically do. Okay. So I'll just give a practical example from my experience. So in undergrad, I worked on a sort of like a robotic submarine project. No, the submarine had a camera right here. Maybe I'll change the color right here. Okay. So, and that's all it had to see the outside world, and it wasn't very good. Like a camera was not enough. It was hard to see things. So one of the objects I tried to see is sort of like an arrow that tells it where to go. I used like a simple mathematical model where, like, okay, we're gonna draw a rectangle around this orange object, and then another rectangle, and measure the angle between them, and that's how we know where to head. Now, this worked pretty well for easy to see objects, but then I ran into an issue where we were trying to see a gate that was really hard to see. I don't know if you can notice it here. There's like a, I'm just gonna outline it. It's like right here. Okay, so it's really, really difficult to see. And there was no way I could have done this with math. I just could not do it. So that was the first time I realized, well, we have to use neural networks, right? So we did. We actually used a neural network to train it to essentially find this hazy looking object underwater. And it worked pretty well. So actually. Let me optimize it for video. There we go. Reshare. Okay. Stop the audio. Okay, so I mean, you'll see here, I'll skip through it, but essentially, you'll see that it does find the gate and goes through it. And that's really all thanks to deep learning, right? We could not use like classical mathematical models to see underwater. It's just too difficult of a task. But this was done overnight. Like literally, we collected, a few videos, went to the hotel room, labeled all these images, and came back the next day, and the neural network worked. Like which perhaps in the past I would have taken years, or if not maybe months, maybe, to actually find the mathematical formula to find these gates underwater. But with deep learning, it happened overnight. So it enables you to do a lot of things. So this was like a practical example in the real world. Now talking about medicine specifically, this is actually another project that I was lucky to be part of at Sunnybrook. So essentially, we had CT scans of trauma patients, where the green parts here are actually implants designed by an AI. So if you remove the green parts, that was like essentially like a broken skull. And then we essentially trained an AI so it looked at implants designed by a company. We were actually working with a company that designs implants. So it looked at these implants that the company designed, learned how to design the perfect implant personalized for each person. And then now, like, you give it a CT scan of a broken skull, and it's instant. Like in less than a second, it generates this implant that you see in green. And you see, like, it fits pretty well on the skull. So it, surprisingly works well. Something I did not expect it to work this well. So this is just an example of what can AI do. Now I'm just gonna talk about a few examples that I didn't work on. So this is just the other two examples were things that I was able to work on. This is just like general. So there's a company that was using AI to sort of triage patients, to help prioritize, who gets to see like what doctor and when, and really help sort of like streamline the process, make the healthcare system more efficient. Another one is essentially AI-driven diagnostics. So sort of like for example, in this case, like an ultrasound machine that you don't have to be an expert to use. So the AI tells you, how to navigate, how to like place the probe properly, etc. Um, Another one is essentially detecting problems in for MRI or CT scans. So you can see here the AI essentially like circling or like drawing a rectangle around the problematic area. And you might say, okay, yeah, this is easy to see, like any person, even without medical training, may be able to detect something's not right here. But and there are other examples where it's like crazy. Even like a doctor would miss it, but it can actually pick it up. Another one is pathology. Like pathology is very popular target for AI. And it can help. And these have been approved by FDA, by the way. So a lot of algorithms have deep learning algorithms have been approved for use by the FDA, even though we can say, oh yeah, it's not super explainable. And we'll get to explainability later on, actually. So I'm just gonna fly through some of these examples. Now, this is my favorite example of AI in medicine. I think this is the fanciest one. Protein structure prediction. So before, it was difficult to predict how the tertiary structure of the protein would turn out given like an amino acid sequence. But now with deep learning, we can literally just give it a sequence of amino acids. It'll tell us how the protein will look like. So you can imagine this accelerates drug creation to like an insane degree. I've even seen recently that where they design sort of like the structure of the protein and just let the AI tell them what amino acid sequence they need to make it. So this is like actually like we're getting to literal science fiction now, where you can like design proteins specifically for a specific receptor for a specific patient, and it can just do it. By the way, the AI that can do this protein structure prediction has the exact same architecture as ChatGPT, just trained on a different task. Slightly modified architecture, but it's essentially the same backbone as ChatGPT. So you can see that this recent innovation just had like an explosion in all sorts of fields. Yeah, other applications, they're like, mining medical records from electronic medical records, drug creation, like I mentioned earlier. So designing treatment plans that are personalized to each patient. This has been used actually, and triaging patients. So like, someone comes into the ER, you can use that to triage them. And this is actually needed. Like all these, there are inefficiencies in our healthcare system that, there's wait times for a reason, right? So all these can help us make this healthcare experience better for patients. So as doctors, I don't think we need to be creating these AIs, but we really need to understand where they can work, how they can help us, because we'll be decision makers essentially on a lot of these things. Now, is there any questions before moving into just a quick overview of how it works? All right. So, and before, classically, we used to invent rules, right? Like imagine Newton's laws of motion. Those are rules. Okay. So we used to invent rules, give get data on whatever, like for example in Newton's motion laws example, like, oh yeah, we get data on the moving ball, and then we can know where it will fall or how fast it's moving, etc. Right? So we create the rules and then we get answers. Now, in the era of machine learning, we don't know the rules, right? Nobody knows the rules. They're too complicated. So we've got, data. We collect a lot of data. You'll hear big data, right? We give answers for what this data means. So remember when I said, oh, you give it a picture of a dog and you tell the AI this is a dog. This is essentially an answer to what the question being, oh, what's this picture? Similarly, you can, you have, pictures, x-ray pictures, and give like medical conditions, give it to the AI and it learns rules, right? So it can learn by itself what the rules are. Now, before we move on to how it works, let's just compare. So Newton back then, he created this law of motion that works everywhere. It works on Earth, you go other planets, it actually models the motion of planets really well. It works surprisingly well everywhere. But if Newton had deep learning, he wouldn't have figured out these rules by himself. He would have done some experiments, collected data into how objects are moving, and then, created a model that can predict the motion of things. But, he wouldn't have understood it as well as when he created the model himself, right? So when he created the law, like the laws himself. So this is a problem with current deep learning, is we don't actually understand how it works, right? You have this very complicated nonlinear function that forms the rules by itself. But it's not, we can't really predict when it will fail. And you'll notice that when you use ChatGPT, sometimes it just gives you straight up incorrect answers, right? And nobody can actually mitigate that. So yeah, it's like it only works on conditions that are similar to those present in training data. So meaning if we took Newton's AI model to a different planet, it just won't be able to predict the motion of objects because it only works on things that are similar to training data. And you'll see that like, oh, there's this new fancy AI that can detect cancers, but it only works at this hospital because it was trained on images from this specific machine, right? Because each machine has its own settings and text like different settings, etc. So that's a drawback of deep learning is, yeah, you don't have to figure out the rules by yourself, but it's also not very easy to understand. It's not explainable. Now, all this fancy deep learning, is based on the model of the neuron that was invented back in the 50s. Now, all it is we've got a set of inputs, right? So, input x1, x2, you can have as many inputs as you want. All these get summed into one block. So this is just adding them together, right? They get multiplied by a weight. So if I had to write the mathematical equation, it would look something like this. It would be like x1 times the weight associated with x1. So you see here the weight. So this gets multiplied by this guy, and then they get added together. So if you'll notice here, we have a summation, another summation, etc., until all. So we sum all these inputs together, right? And then so after we sum them, this goes through an activation function. It's just a fancy term. It can be anything. It can be just a linear function, meaning it's the exact same as the input. And you get your output, your essentially your function, right? So remember back to y equals f of x. This is essentially it, except x is the summation of all these together. Okay, so lots of things getting summed together, and that's what the neuron does. And you can, people call it neuron because they see some connection to our biological neurons, which kind of makes sense. You got different cells connected together, and they're all like connecting to this one cell, and the potentials do add together, I guess. So that's what the basic neuron does. But then we hear like, oh, ChatGPT has like a few billion neurons. So how do you mix these neurons together? Well, the simplest way is to get one of these neurons and add more of them, and then use the subsequent neurons as inputs to more neurons. And you can keep adding more and more and more layers and more neurons, right? So each circle is a neuron, and it's also an input to the next layer. So if we look at the mathematical formula here, y1, so this guy, right? You see how there's 3 arrows coming at it from each one of these inputs. Okay, similarly, we have these 3 inputs here, okay? And then Z1 right here has 4 arrows from the Y layer. So you'll see that has 4 summations in the equation that I wrote here. I can pause, guys, please ask me questions. I'm not gonna spend too much time here because, oh yeah, what's up, Yasin?
So it's like I had a quick question, probably not related to this, but in general, so you have a model, you're giving it your input and your desired answers, right?
Yeah.
And then you hope that when you give the input in the future that you get your desired answer.
That's correct.
Okay, so can you figure out what the rule is that the model uses to get from your input to that desired answer?
Yeah, 100%. So you see these weights that I'm multiplying by the inputs, and
Yeah.
actually literally write it down, right? So this is a pretty simple neural network that we have here. And yeah, you can actually figure out the exact equation that this network is learning, right? So there's nothing, they say, oh, it's a black box, but in reality, it's not really a black box. You can actually sit down and write every single equation that's coming out of this network, right? And you can actually try to understand, okay, yeah, I see what's happening here. The problem is when you scale it to like millions and billions of neurons, then it becomes really, really difficult, right? Becomes really difficult to write it down and understand what's happening there. So the only problem with the explainability of AI is that it's really big. It's really just a lot. There's a lot of things going on there, right? So yeah, you can actually sit down and try to understand it, but it's just too much time. It's what we call in computer science an intractable problem. Means like just it takes too many resources, too much time. You can't really be bothered with it.
So so I understand that. So it's hard to conceptualize like what you're talking about with just like variables. When you're talking about these variables, is it like a number associated with like the importance of a certain factor, I guess?
Yes, exactly. Yeah. Thanks for
Okay.
asking that. Yeah, actually. So let's say X1 maybe is like your heart rate. It could be your heart rate, right? And then this could be your rest rate. Okay. And this could be, I don't know, blood pressure, right? And this network could be learning your sulfate criteria, for example. You see what I mean? Uh,
Yeah.
yeah. So like your inputs can be anything. That's what's so powerful about neural networks. You can give it any number of inputs, and if there is a relationship between them, then it can learn these relationships. And that's why you see like a lot of crisscrossing. Actually, I wanted to show, I know this slide is actually very technical. You guys shouldn't be bothered with it, but I wanted to show it because it gives you an intuition into all the crisscrossing that happens, all the relationships that are forming between these variables. So does that make sense?
Yeah, a bit more. Yeah.
Yeah.
Thank you.
Yeah, and this W here that you see, W1, W2, whatever. This is really just how strong the connection between X1 and Y1. So the weight is just how strong the connection is. So the higher the weight, let's say it's between 0 and 1. If it's 0.5, yeah, there's some connection. If it's 0.9, you're like, oh, there's a lot of connection here. And those in neuroscience may have heard neurons that fire together, wire together. Do you guys hear that before? Um, where like the way we learn is there's associations between different neurons in our brains and they start firing together. There's all these theories. Um, pretty interesting. So this is just an overview here. Again, we give the network like an image, for example. An image can be a few thousand pixels, right? So we give those pixels as inputs. We say, oh, these pixels are a cat, these pixels are a dog, these pixels are a cat, whatever. And then it goes through this sort of like connections, right, that we showed in the previous slide. And then at the end, you just have a very simple decision, right? Is this a cat or not, right? And then given how good the prediction is, so let's say it was a cat, but then the network predicted it wasn't, there's feedback that happens. So like if it's wrong, you're gonna have a feedback here, and it's gonna be like, okay, no, you see, this was incorrect, so you need to change your weights. And we're not gonna talk about how these, weights are changing. But all I wanted you to know is, if it's gonna try to do something and if it's wrong, It's just not, it's gonna change it until it works, right? So it's gonna be like this iterative feedback loop that like, oh, it's correct, good, the connections are good. If it's wrong, oh no, change them. Yeah, someone raised their hand. Yeah, Juliana.
Hi, Hamza. So for this picture, I guess, is this considered then supervised deep learning, or is deep learning a separate like category?
Yeah, that's correct. So this is
Okay.
supervised deep learning, yes, because
Okay.
you're telling it, yeah, this is correct, this is not correct. The moment you're telling the model, okay, this is correct, keep what you
Mhm.
have, or this is incorrect, change what you have, it becomes supervised.
Okay. And so is it also like, I guess they don't have to be in their own silos, but is this also reinforcement then if it's, or is that completely different? We only barely touched on it because you're saying it goes back to adjust,
Yeah,
but it's
so reinforcement learning is more concerned with actions rather than just predictions. Um,
okay.
yeah, so that's why, like, you know what, it's not gonna be very useful for doctors, at least not in its current state.
Okay.
Yeah, I mean, it is the same, I guess it's a similar idea, but it's not the same. I don't want to go too much into details, but yeah, you are correct. This is supervised deep learning, and most
Oh,
medical applications will use something like this.
okay. Thank you.
Thanks. Yasin, you have, oh, you still have your hand raised. Is it the same one?
No, it's a different one.
Oh yeah, what's
All
up?
right. So you have your initial input, every pixel of the image, and then your end result is this a cat, right?
Yeah.
But the intermittent questions of like, let's say, for example, is this a circle? Is this a line? Is
Yeah.
that determined by the model itself, or are you feeding like stepwise like questions or like flags along the way?
Oh, do you mean like, oh, to detect a cat, you need to detect like the circle that is the
Yeah,
pixel?
yeah.
Oh yeah. So actually the model figures this by itself, right? So we can kind of plot what's happening to understand, oh yeah, it's trying to find lines here, trying to find circles here. But we don't really care about that. Like, I mean, you can care about it if you're a computer scientist, but as an end user, all you care about is the output, right? So all this in between here, we don't really have to, like, as humans, we don't actually have to understand what's happening. I mean, it it would be useful to understand what's happening. Let's say you're trying to find like a certain disease process and trying to figure out how this network is detecting a disease. So then it would be good to try and understand it. But it's not necessary. It's not like a necessary step of the learning process, right? The network by itself figures out features such as, oh, is this a line? Is this fur? Is this whatever?
So essentially, it finds out like the predictable patterns
Yeah.
ultimately to its own. Okay, cool.
Yes.
Thank you.
Yeah. And the math behind it is actually so elegantly simple. But we're not gonna go into it, but it actually it just works. That's all I can say for now. At least
Sounds good.
yeah, for this workshop. I don't want to go into details. All right. Okay, so yeah, this is just an animation. You so after it works, like once you train a good neural network, you should give it like an image, right? It should activate the neurons, and if they're activated in just the right way, it will give you the correct answer. Okay, so this is essentially how a neural network works in a nutshell. Okay. Now here's a bigger one, a bigger network used for detecting hand digits, right? So they've given it here the number 3, right? And it predicts, oh, it's a 3, it's a 7, it's an 8. So this is bad, right? So we essentially need to look at, what it got right, what it got wrong, and then it will provide feedback to the network. So this is how it works. You see how it's essentially, oh yeah, it passed an input, it predicted it wrong, so it's giving feedback to all the layers sequentially. Okay, so we don't have to actually know how it works, but this is what we describe as training. So if you ever hear, oh, the network is training, it means it's just going through these iterations of oh, it's doing it, it's got it right, it's got it wrong, and it's getting feedback to adjust its weights. Okay. And then once it's trained properly, it should again activate in just the right way to activate the final output that's associated with your number. Okay. So that's like a fully trained network here. And I really love this visualization here that actually shows what's happening once you have like a trained network. So you'll have here again images that are being fed here. Okay. So here, what it's showing, what this video is showing, an image. Okay. So I've got an image, and it's passing through these layers that we talked about before. And you'll see that's actually activating different parts. Each number is activating different parts of the network. So somehow, certain neurons become more likely associated with a certain number, and then it's able to detect, oh, this handwriting that's a little weird. It's a little different from the 5 I saw before, but it's close enough that activates the region associated with the number 5. Then it predicts, okay, this is the number 5, and so on. So this is really cool. This is actually, so when they say, oh, you can't really explain neural networks, like the decision making process in the neural network, where you can, it's just difficult to visualize. So this is a very simple example, and you can see it's still actually a little difficult to visualize what's happening, but it is possible. Okay, it's just more difficult. Okay. Is there any questions on this visual, or good? All right.
Hamza,
Yeah, what's up?
so does this mean that neural networks can only output discrete values? Like what we're seeing here, 1 through 10?
Yeah, so this is a certain architecture that can only output, these discrete values, but different architectures may allow you to output continuous numbers that are in different sizes, essentially, right? But they all work off the same principle. That's actually a really good observation. Yeah. So, classically, yes, you can only output a certain number of like a certain number, like you can only have a certain number of outputs. But that is changing with certain architectures. Like there are image specific architectures that can actually scale up depending on how big the image is. Okay, but then it also comes at the disadvantage of certain things don't work unless you have like a specific structure. Does that make sense?
Yeah, thanks.
Yeah. All right, so yeah, it's like you mentioned, we're just gonna go through like the major class, and we're almost done. So we're just gonna go through the major classes of neural networks. That the first one I'm gonna talk about is ones that are good for image processing. We're not gonna go in detail. I just want you guys to know this term here, convolutional neural network. So whenever you see this, just think images. A lot of medical imaging research hinges upon convolutional neural networks. So these are networks that are really, really good with images, really, really good with images. So for example, here we have a picture of a koala, and then at the end, we have a prediction, oh, is this a koala or not a koala? And then just remember, if it's a medical image, and like, oh, this is a disease, is there cancer, is there no cancer here? Or it could be anything, really. Yeah. So these convolutional neural networks also are used widely in self-driving cars. So for example, an input would be this image, and then the network would tell you, oh, there's a stop sign here. Similarly, it could highlight cancer in an X-ray. Next is there are networks that are specialized in sequential data. So we learned, for example, that a single X-ray may not be useful you may need actually sequential X-rays to be able to tell, like, to be useful. This type of network essentially hinges on sequential data. So we've got, you'll notice here, oh, input at, time -1, input at the current time, and input in the future or whatever, right? So we have inputs at different points of in time, and these give you essentially, they all feed into each other to give you like a certain output. So these are actually most used in stock price prediction, because stocks, oh, it's not just enough to look at what's high, what's low in the market now. You need to look historically what was high, what was low, and the patterns between them. So these are networks specialized for these. They're called recurrent neural networks. Next are the networks that are used in deep fakes. If you've seen deep fakes before, these are made by something called generative adversarial networks, or GANs for short, as GANs. So these work by essentially like you generate a fake image, okay? And you also generate a real image. I mean, not generate, you have a real image, and you tell the model, like, okay, which one is real and which one is not. Okay, and so we have two neural networks at work here. We have one that tells which one is the real one, and we have another one that's generating the fake image. And if you think about it, in a training process, they're both getting better by working together. So the generator network gets better at faking, because it's trying to trick the network that's trying to discriminate what's real and what's not. And then the discriminator network is getting better at learning what's real and what's fake with this feedback process that we're doing. So both networks get really good at what they do, and the better one network gets, the better the other one gets. And that's how we get really good deep fakes that look like real humans, right? Yeah, so there are actually applications in medicine, and we'll get to this is pretty cool. So again, these are networks, these scans, they're used in deep fakes. I'm sure you've seen like these videos before. Very scary. Now, deep fakes, they're useful in medicine because you can do things like if you have a low resolution MRI or CT or whatever, you can generate a fake higher resolution image. Or for example, if you've taken an image of like the eye vessels, you can generate a fake fundus image. Or something that's actually quite controversial, but some people were able to synthesize MRI images from CT scans, which you can argue, yeah, there are features that that are correlated between these two imaging techniques, but in the end, this image that you're generating is a fake, it's not real, and that's very important to keep in mind. I think it's useful because we're generating networks that understand important information, for example, in MRI images, and then extracting this information to generate a pretty good CT image means it actually understands what's happening in the MRI. So there is definitely value in these. Just controversial because you don't wanna go on like fake data in medicine, I guess. Now, next, and finally, the last architecture we're gonna talk about is a transformer network. So again, remember all these architectures that we're discussing, they all use neurons as building blocks in them. They're just arranging them in a differently, essentially. They're arranging them different, and they call them different architectures. So specifically the transformer, very, very impressive architecture that started, was published in 2017, like I mentioned earlier. It's responsible for ChatGPT, GPT-3, like BERT, which is essentially a translation AI. You can give it any language and it'll translate it to any other language really well. And then remember the protein folding AI that I mentioned earlier, where you have like your amino acids and predicts the folding structure of the protein. So all these were done by transformers. Their transformers seem to be magically good. We don't fully understand them yet because again they're recent, but they're working pretty much in every application. They're working really, really well. So it's good to know this keyword transformer for future. Now we're done. Just some keywords to be aware of as doctors. Explainability, right? So, understanding that it's very difficult to explain the thought process of a neural network. We can try to visualize it like we saw earlier, but that's not necessarily the case, especially when you have billions of neurons. We have to think about human AI interaction, and that means, us as doctors, how will we be using AI in the future? How will patients use AI? Will it help them, choose which doctor to go to? Then we need to think about the quality and quantity of data. So there's something called garbage in, garbage out in data science. Is like if you feed garbage data, you're going to get a garbage model. So, we need good data and high amounts of data to avoid bias. The next keyword, bias. So bias exists everywhere, obviously. It's you can't really get around it, but by having more and more people contribute to your data sets, right? So let's say having people from different races in your skin cancer detection algorithm, that can try to overcome your bias. The next keyword we're going to talk about is overfitting, and that's when your AI gets really, really good, but only on the data that you're showing it. So for example, think back to the CT scanner at the hospital, where like you have an AI model that works really well on that CT scanner. It can tell you if there's a cancer or no cancer, but then you take the same model to a different hospital, it may not work because different patient population or different settings, etc. So we call that model overfit because it overfit for the specific application was used in. And finally, we're seeing that right now with the lawsuits with like the image generation AIs. If you've seen like these artsy AIs that generate really cool images, but then there's some copyright lawsuits because the AI was trained on many artists, like on like drawings from many different artists. So there's all these legal issues that we have to think about, and liability. If we start using AIs more in diagnosis, where does the liability fall? So these are just some good keywords to have in your vocabulary if you ever get interviewed, I don't know, fourth year, and they ask you a question. These are good keywords to use. So back, I'm just a quick discussion, just want to hear your thoughts. So think back to, classifications of narrow AI, the artificial general intelligence, and artificial super intelligence. We definitely don't have a super intelligence yet. But with, ChatGPT coming out recently, do you think that ChatGPT could be considered artificial general intelligence? Now, it works for many different applications, whether it's like, write an email for you, write a poem for you, or like just answer your medical question. So what do you guys think?
I'm so sorry, Hamza. I have a question for you from a couple slides ago.
Yeah.
It was on the generator and discriminator slide, and you mentioned how sort of like the generator benefits from the discriminator and vice versa, like they're just building each other up to a really high quality. So
Yeah.
if we had like a ChatGPT discriminator, like a sort of like a plagiarism checker for ChatGPT to see if ChatGPT is fake, then as long as ChatGPT improves, will this discriminator always be able to catch up to discriminate ChatGPT's plagiarism?
That's a really good question, and I'm sure that's how they got the how there's detectors for, oh, is this text generated by AI or not? I'm sure this is how they're doing it. And yeah, it's true. It's, as long as the generator gets better, if you have good data to tell, oh, this is plagiarism, this is not plagiarism, then your discriminator will also get better. So, using this, you can actually train a really good plagiarism generator, I guess. Did I answer your question?
Yes, that makes sense. Yeah, that's in some ways that's like it's reassuring, but in some ways it's also like sort of scary how ChatGPT can just like always keep on getting better.
Yeah, it can definitely get, we don't know how much better it can get, right? So ChatGPT is based on this model here, GPT-3 that I mentioned. And GPT-3 was created in 2019, right? So ChatGPT is actually old technology. There are rumors that OpenAI already has GPT-4. We don't know much about it, but I guess when they release it, it's going to be like, I guess, even crazier, because ChatGPT is so good and it's like a few years old technology, right? So just imagine, there's a YouTuber that says, don't look at what you have now, think what you'll have 2 papers down the line. So, it will get better probably. And this is actually very creative. Your question shows like really creative thinking, or like all these architectures can be mixed together, right? So transformers can be put into the generative neural networks, and different like convolutional neural networks can be mixed there as well. So everything I showed you like can be mixed together. So they're just ingredients that you can use. All right, so back to the discussion. If anyone has, thoughts, do you guys think that ChatGPT is narrow AI or general AI? Anyone wants to chime in?
I think it would be general. Like it's not gonna be super. 'Cause
Yep.
remember we did that one respirology question, that one math equation, it messed it up.
Yeah.
Yeah.
Yeah, so yeah, I mean, I actually would argue that it's not even general yet, because all it does, it completes text inputs, right? Like it actually, it doesn't actually, you could argue that understands what you're talking about, but even if it does, it can only do one thing really, really well, which is complete text, right? Like it learned math through text completion, but even that math, like when you ask it to solve a math equation for you, it doesn't always get it right, because it's not trained to do math, right? It's trained on one thing and one thing only, which is to complete text, give you like the most likely text that comes next. But yeah, I mean, I think it's edging between, general intelligence and narrow intelligence. I think it would be maybe somewhere like here. That's my personal opinion. I've seen people argue that it's AGI, it's artificial intelligence. It's definitely not just narrow. It can do many different applications at the same time, but I don't think it's artificial general intelligence yet, because I wouldn't describe it as being human-like in its intelligence. Yeah. Yeah, I mean, there actually is a generalist AI that was released by Google last year. It didn't get much traction, but can do 600 different things. Like you can give it images, you can give it text, you can give it video games, and you can actually let it control robots. It's actually crazy. So it was designed to do like these 600 different tasks and does them pretty good. So I just wanted to mention it on the talk of generalist AI. So it's cool. Okay, so we're done. Thanks for sticking with me. So I know it's a long workshop. We're just gonna do a quick demo. And I actually will share these links with you so you guys can follow along at home if you want. You can also just watch the screen. You don't have to actually do it. But I'll send it in chat. Where's the link? Is there no chat? Like, did Western disable chat?
I think you have to enable it yourself.
Ugh, whatever. I'll just send it on.
You can post it in the event if it's a link.
Yeah, I'll just post it in the event. Actually, that's a good one. That's a good idea. Yeah, I'm not sure if everyone has access to the event, but here. Just gonna. So we're gonna play around with a model called BioGPT. So this was released recently by Microsoft. It's essentially ChatGPT but tuned on PubMed. So specifically for biology stuff. All right, did everyone get it? I mean, if you didn't get the link, it's okay. We're gonna do it here. So what you'll open is something called a Python notebook. Okay, there's already the code is already there. All we need to do is run it. So what I would do, if I were you, I would. So once you open it, I would go to runtime, change it to GPU, because if you don't use the GPU, it'll be very, very slow. So just chime in. And then to run the code, you're just gonna click run here. Okay, so what it's gonna do initially is just install some stuff for us. So it's just essentially what it's doing is, because we're running this on Google's servers, they don't have the stuff we need, so it's just installing, like it's downloading code and like installing it on the Google server. So nothing fancy here. I know it outputs a lot of things. It feels like a hacker thing, but they're just downloading things. So once it's done running, we're just gonna click on the next part here. So this next block of code, what happens? It's essentially initializing this massive transformer network that we talked about. So it's just gonna be like churning in to initialize, and you'll see it's downloading stuff. So it's just, again, it's the first time you run it, it's gonna download it. It's downloading like a 1.5 gigabyte model, but luckily it's on Google's computers, so they can take care of that. Okay, so what's happening here? It downloaded the model, and all that's happening is just initializing. So now it's ready to use. Now we can actually give it a. So I'm just gonna say, oh, COVID-19 is, and we'll see what it completes. And I'm gonna ask it to give me like 5 different answers. Okay, so let's just see what it does. Okay, so here it says, oh, COVID-19 associated with the risk of HIV seroconversion among, I don't know, do we have any second years that can tell us if this is true? I have no idea. So you'll see here, oh, it's one of the largest viral epidemics around the world. It's a common condition affecting 17 million people. So increase inflammatory markers, etc. So all it's doing, it's completing text for me, right? So think back to ChatGPT. This is just like that, except ChatGPT was fine-tuned to chat with you. This one just completes text, right? Does anyone want to share an interesting prompt that they did?
What's the extent you can use this for, other than just like completing sentences? Like
Um,
like a useful thing that you've noticed?
I mean, you can, so actually, perhaps not specifically here, but in chat, not for this model, but for ChatGPT, for example, I've been actually giving it some of our DSSG cases, and it kind of actually explains the thought process behind what's happening. So, if you go to ChatGPT, here, like I've literally been asking it questions like, oh, give me this formula, what does it mean? Here's this case, can you like explain it to me? All that stuff. So this is, I guess, the practical use for these things. Now, for us, specifically here, I wanted to give you guys a taste of how to use, I guess, like a non-end user product, like actual code. So you can actually use this in research. So for example, this network doesn't just do generation, right? It can actually classify things for you, because it understands English language, but also understands medical language. So you can use it you can actually take the same network, but train it a little further to do something that you want to do. Okay. So for example, you can take this same model and train it on like reading a referral from a physician, and then classifying this as high risk or not high risk, for prioritizing which patient to take first. Does that make sense?
Yeah.
So that's
Like that you would have to modify the code for that, right?
you would, yes. Yeah. But it's actually like you can see how little code it takes for us to like run this, right? So it's actually not a lot of code, especially in Python. And it's very accessible because you don't even have to run it on your computer anymore. You can just run it on Google's servers.
Hey
Yeah.
Hamza, I have a request for your BioGBT.
Yeah.
Can you ask it what the cure for cancer is? Or like the cure for cancer is I just want to see what type of like
That would be interesting.
results.
I think ChatGPT would probably give us much better output. But we'll see here what this does. This is incorrect. Yeah. So again, like I wouldn't call these good outputs, these models, again, their goal, like this specific model was trained to complete sentences, right? It's not trained to give you accurate information. It's not trained to like respond to you in a sort of like conversational way. ChatGPT was actually trained to do that. So like if we take the same prompt and paste it there, it probably will be better, even though ChatGPT was not trained on medical data, like specifically, just was trained on the entire internet. So you see this output here as AI model, I can't claim there's a single cure for cancer. This is actually not the original output of the model. They add this because they don't want to get sued. But here you start seeing the real answers from it, right? So there's been significant, etc., etc., etc. And you can ask it, like, okay, tell me more about, chemotherapy, for example. So ChatGPT is great because it actually takes in the context of the questions you asked before and the answers that it gave you, right? So it's not just taking my question as input, it's taking the entire conversation as input, right? So it works a little better than this. But ChatGPT, we don't actually have access to it. We can't really use it in research because it's not open source, but this one is. So this one we can actually fine tune to do useful stuff for us. Right now it's not very useful. It's just a model that understands medical language. But it's a blank canvas that you can actually use. Does that make sense?
Hi, so I have a question.
Yeah, what's up?
So has anyone been using, like, I guess, this stuff for systematic reviews? Because it's kind of like it's like there's a process or a sequence to it, right? So it seems like it would fit well to
Yeah,
that.
yeah, 100%. I think I've seen papers where they're using it for that, right? So let's see here. Transformers for systematic reviews. I've seen actually an hmm, I'm pretty sure actually I've seen models that are actually designed for that. Maybe I can't pull up the paper now, but yeah, you're 100% right. This is super powerful for things like that, right? You have it like go through all the literature and summarize it for you, right? And this is actually
Yeah.
something that these models work really well for. So for example, let's say we give it like you can actually give it like an entire paper and ask it to summarize it for you, and it will do it. So it's pretty cool. Yeah,
Thank you.
yeah. All right, so we'll move on to the next demo. I'm not gonna so I'll share this link with you guys if you wanna run it. So again, you don't have to write any code, you just click run, run, run. And I have like things explained here. But essentially we have this database of like x-ray images, okay, and they're labeled no pneumothorax or pneumothorax. Okay, so I've got this, I think is like Excel file. You get like the first image is not pneumothorax, second image is, etc. Okay, and then so they look like this. Okay, and then I initialize a convolutional neural network. So if you remember, these networks are really good at they're really good at images. So they learn pretty good. So here we train it for one cycle, meaning that it just goes through the data set once, learning, okay, this is new pneumothorax. I'm gonna modify my approach a little. So it goes through all these images, modifying its approach each time. And you know, it actually does pretty good. So here you can see the model. The top is the actual ground truth, and then the bottom is the prediction. So here, you know, it predicts that it's not a pneumothorax, not a pneumothorax, predicts that here is a pneumothorax. So you know, it gets a lot of them right, but some of them not so right. So then we train for 20 more cycles, which also is not a lot, by the way. This takes like maybe like 5 minutes to train 20 cycles, which in the machine learning world is not so good. But you can see the accuracy improving. So see here, accuracy, it's improving. So if I ask it to classify again, it actually gets more images correct. So in just like a few minutes, you're actually able to what is it, like get a model that can actually read x-rays and get pretty good classifications, right? And all it is, we literally just have the image and an Excel file that is saying, oh, this image is not pneumothorax, this image is pneumothorax. That really is all there is to it. It's that easy, right? So, you know, as a researcher, maybe you could think, oh, I'll just, you know, acquire the images, label them with my medical expertise. Maybe you can hire like an undergrad, even some high school students who do coding can do it for you. You know, you shouldn't be too concerned, I guess, with the coding, but understanding that you can actually do these things with AI is important. Yeah, and then you can, you know, do statistics like a confusion matrix, calculate your sensitivity, specificity, all that stuff. Yeah, so I mean, I could like like actually run this demo, but I think you guys can just run it on your own. I'll share the link with you later. We're running pretty late, so I guess it's better if we just have the floor open for questions. All right. If you guys don't have any questions, I guess
Sorry, I have a quick question, Hamza.
yeah, what's up?
So I don't know if you've already talked about this, and like I don't know if you've had another AI event already, but like to play around with some like simple models and stuff, what do you recommend? Like what language would you recommend? Is it Python?
Yeah,
Is it
Python.
okay?
Python. Yeah.
Thanks.
Yeah, so like yeah, I purposefully use these like here in Python, and I wanted to introduce you to this like Python environment that lets you like
Yeah.
because it's actually you can see it's I know it looks like techie and whatever, but it's almost like English. Like Python is actually, as far as programming languages go, is actually, pretty close to English. Yeah, so if there is enough interest, I could do like an actual practical workshop where we go through something from scratch, like an easy example. But maybe I'll send the survey later to see if there's interest in that.
Okay, sounds good. Thank you.
And meanwhile, if you guys need I guess help, if you want to do AI and need help, I'm happy to help. just reach out to me privately, I guess. All right. I think that's it. I'm just gonna stop.